A toy manufacturer makes models of submarines and helicopters. His factory has the capacity to produce a total of 1,200 toys per week. His supply of plastic is limited to 2,200 litres per week, each submarine requiring 1 litre and each helicopter 2 litres. He sells at least twice as many helicopters as submarines. We want to write 5 inequalities from the given information, so our first step is to define our variables. So if we let S be the number of subs and H be equal to the number of helicopters, then from here we can see that S plus H has to be less than or equal to 1,200. The total number of toys made can be 1,200 or less. Now for the second one, the supply of plastic is limited to 2,200 litres per week. A sub requires 1, helicopter requires 2, so he's going to use 1 litre for every sub, so S litres if he produces S subs. But each helicopter requires 2 litres, so if he produces H helicopters, that's going to take 2 litres, 2 H litres, 2 for each one. So that's got to be less than or equal to 2,200. Now if we come to here, so if S is the number of submarines, he can sell twice as many helicopters, at least twice as many helicopters, so that's the same as 2S, or more than 2S. We also know that he can't produce a negative number of each, so the final 2 inequalities are the non-negativity ones. We now want to plot the inequalities on the grid below and shade the feasible region. So the boundary for this one will be S plus H is equal to 1,200. So when S is 0, H is 1,200, which puts it just here. If we have that H is 0, S would be 1,200, which puts it just here. And then we can draw a straight line between those 2 points, like so. We really ought to label it. So this one is S plus H equals 1,200. And we know that we need to be on this side of that. Now, the next boundary is S plus 2H is equal to 2,200. If S is 0, 2H is 2,200, so that would give us H is 1,100. So that's just here. And if H is 0, S is 2,200, which is all the way out here. And then we need to join those 2 points like that. And we need to be below. And finally, H is equal to 2S. So if S is 0, H is 0. If S was 500, H would be 1,000. So that's going to put that just there. And a straight line through those. So we didn't label this one. So this one was S plus H, 2,200. This one is H equals 2S. And if H is going to be bigger than 2S, that needs to be in this direction. So we need to be this side of this line and below these two, which means that the feasible region is this one in here. Now we need the vertices of the region. It's not always easy to find these when you have such coarse grid paper, and they certainly give you paper like this in the exam. But usually this comes up on the calculated paper, which means you can find the vertices accurately by solving simultaneous equations on your calculator. But anyway, what we have here is 0, 0. This one up here is 0, 1100. There's an intersection just here, and that one is at 200, 1000. And there's one here which is at 400, 800. So those are our vertices. Now he makes a profit of $2 per submarine and $1 per helicopter. State the objective function. So if we use P for profit, he's getting $2 for every submarine sold and $1 for every helicopter. So his profit function is going to be 2s plus h. How many of each toy should he make for the maximum profit? So we know that P is equal to 2s plus h, and we need to evaluate that for each of our vertices. So we need to evaluate the profit at each vertex. So this one's going to be 0. 2 zeros, add 1, 1100. 2 lots of 200, add 1000. 2 lots of 400, add 800. So this one's the best. So what we should do is produce 400 subs and 800 helicopters, and that would give us a profit of $1,600. If the profit on a submarine was to slip to 50 cents, how many of each type should now be manufactured in order to maximize his profit? So the profit function is now 0.5 s plus h. So that's what we need to evaluate at each of our vertices. Okay, so doing that, this one's obviously going to be 0, 1100, 1100, and this one is 1000. So these are the same. Now, note that these lie on this boundary just here of the region. So in actual fact, we'll get that same value at any integer valued points along this line. So that means that we have multiple solutions. To try and explain why, we've been solving these problems by point testing. There is another technique, which is you get the profit line and you just plot it on here. So we can plot it on there for a particular value of P. You then increase p, which means that this line will move, since its intercept is changing, across the region. The last point, which is left inside the region as the line sweeps across, is the vertex at which you get your maximum. So in the first part, we had a profit line that had this gradient, and we swept it across the region, and this turned out to be our last point. But this one that I've just put on, which is this one, as we sweep that across, this is actually parallel to the line we have here, so it meets not just a vertex, but a whole line as the last thing, and therefore we get a whole line of solutions.